Yeah, sure. The first time that I experienced lateral torsional buckling, it was when I was a freshman, or what we call a plebe at the military academy. And they have this water obstacle confidence course. And they have this wide flange shape about 20 feet above a lake. And it's about 40 feet long. It's only about 6 inches deep. And they make you walk across it, right? To make yourself confident that you can balance on a beam. The flange width on this thing is probably 6 inches. But then at the middle of the beam, you have to walk over a staircase and go up 2 steps and back down and then out. And so when you get up on that top step, you can feel that beam start to shake and move underneath you. Now, it was probably a little bit of the motion in my knees that was helping that, but also, that lateral torsional buckling behavior, when you push down on a beam, and this is a very slender, long and thin beam, when you push down on that beam, that top flange is going to go into compression. And based on its initial imperfection, it's going to want to buckle one way or the other. And so often in class, we kind of do what we call, there's a fancy word for you, bifurcate the problem, right? It's like it's either doing it or it's not. Well, that's really not the behavior. The behavior is it starts, right? It starts slowly and then builds until it gets to a point to where it becomes unstable. That's what I was feeling. As a matter of fact, when I returned to the faculty years later, one faculty member said they actually did the analysis and, about a 200-pound person would really start to feel the effects of lateral torsional buckling on that beam. But anyway, that was my first experience with it, was actually feeling it, right? Fast forward about 20 years later, we had a TxDOT research project. We were looking at skewed steel girder bridges and warping restraint. So I got to build a full-scale model with 3 W30 by 90 wide flange shapes. And if I remember right, the length of these, the unsported length, was about 35 feet, right? So we had designed these things such that they would go into elastic lateral torsional buckling. We started with just twin girder tests, 2 girders side by side, and they weren't skewed. They were just perpendicular to one another. Well, they were aligned such that the ends were in the same plane. And so we would apply a vertical load on the top flange, and you'd watch the behavior, and it was just like you would imagine. That top flange starts to buckle out. That causes translation and twist to the cross section because that bottom flange is in tension. It wants to try to stabilize through the web, the top flange. But what you really get is you get the top flange bending one way and the bottom flange bending another. And somebody named Morris O'Jalvin in 1977 said, hey, what if at the end of the beam, if we're getting bending on the top this way and bending on the bottom this way, what if we just put something to beef up that web in between to try to brace one flange against the other and keep that bending from happening at the end of the beam? And that was the research project. So we tested without anything at the ends of the beams, and then we tested with a pipe stiffer. So imagine splitting a pipe in half, welding it to either side of the web at the beam end. Now, if this guy tries to bend one way, the other guy tries to bend the other, they're going to brace each other. It's a very strong brace, that closed circle. That did improve the load that we could put on that without lateral torsional buckling occurring by about 70% on those beams. But you could see the lateral torsional buckling occurring. I had felt lateral torsional buckling earlier walking across that beam. Now I was in the lab knowing that I was seeing it. And you also learn a lot of other different interesting things about how to try to model real behavior in the laboratory. Just a quick example. We had to use these things called gravity load simulators because if you pull down, well, if you have that force anchored into your lab floor, it's always going to want to try to stabilize the force. Whereas where I was walking across the beam, there was nothing connecting me to anything else. So that beam was free to move as it wanted. With these gravity load simulators, they allow that vertical load to translate with the beam and better simulate that actual vertical load on the beam, on the top of the beam flange. So, just some interesting things you learn in the laboratory. And, things like load height effects, how far you apply that vertical load from the center of your shape also impact how lateral torsional buckling works. When I stepped up on those 2 stairs, that was bringing my load a little bit farther above the center of gravity of that shape, and that enhances the lateral torsional buckling that may occur. So we have these things called load height effects too that, you don't read about some of these things in the code because, quite frankly, only in very special situations do they matter a whole lot. In codes, we have to make decisions about, balancing simplicity for practitioners and complexity to make sure that we account for things, that are important to our structures.